Hello guys, today in this video we are going to discuss about Compton's effect or Compton scattering. So in 1922, um, the American physicist, okay, his name is Arthur Compton, okay, and he was investigating the scattering of X-rays, okay, by different substances, and he observed that the scattered X-rays, in addition to radiation of the initial wavelength, okay, in addition to this radiation, the initial wavelength of wavelength lambda of the initial, the X-ray, okay, also contain rays of greater wavelength lambda prime, okay. So this phenomenon is known as Compton effect. The difference between these two wavelengths, okay, lambda prime minus lambda, is known as the Compton shift. Is known as Compton shift. Okay, and it was found that this del lambda depends only on the angle theta that is made by the direction of the scattered radiation with that of the initial beam. Okay, the value of del lambda, this del lambda, also doesn't depend on the wavelength of the incident radiation lambda or the nature of the scattering material, okay, through which it is scattered, the X-ray is scattered. Okay, so now, since the scattered radiation contains wavelength other than the incident wavelength, right? This phenomenon is also known as incoherent scattering. Incoherent scattering we call it, because it is having one more, another value of lambda, which we said lambda prime, right? But as per classical theory, or the classical model of radiation, right? The radiation contains oscillating electric and magnetic fields. We know that, the electromagnetic radiation is actually having two components. This is your electric field, this is the magnetic field, and the direction of propagation, right? So consists of oscillating electric field. Here in this direction, suppose I will say this is the oscillating electric field, and your magnetic field will oscillate perpendicular to it like this, right? So perpendicular to this. So this is your electric field and this is the magnetic field, and the direction of propagation is this, right? So here, so we said radiation consists of oscillating electric and magnetic fields. So when such a radiation is incident, this electromagnetic radiation is incident on a target, on a matter, okay, in which there are loosely bound electrons, okay. So what will happen, these electric field, okay, will exert a force on those loosely bound electrons, and these loosely bound electrons will begin to oscillate with a frequency that is equal to that of the incident radiation. So you have this incident radiation, your electric field is actually oscillating, right? Oscillating force, F is equal to QE, we said F is equal to Q times E. So the electron will also experience, as the electric field is oscillatory, the force will also be oscillatory. So the electron will also start, oscillating with the same frequency as that of the electromagnetic radiation, right? And in doing so, what will happen, these electrons are the charged particles, so they radiate electromagnetic waves. So they will radiate, this electron, oscillating electron will now radiate electromagnetic waves, and the frequency of those radiated electromagnetic waves will have the same frequency as that of the incident one, as that of the incident radiation, right? So the classical picture of radiation predicts the presence of only one unmodified radiation, okay, that is only one value of lambda. So this lambda is exactly equal to the lambda of the incident radiation, right? And we call this as Thomson component. Thomson component, right? So the presence of this longer wavelength, which we said lambda prime, which is greater than the value of lambda. So the presence of this Compton component or the longer wavelength, okay, which we said the modified or the Compton component in the scattered radiation cannot be explained on the basis of your wave model of the radiation. So how to understand the Compton effect considering the quantum effect? Because we can see that using the classical model of uh, wave, you won't be able to actually explain this longer component or the Compton component, right? So using quantum theory of radiation, we can clearly explain the presence of this lambda prime or the modified wavelength that we got in the scattered radiation. Okay, and from where we got, what is the source of this lambda prime, how we got that, can be explained. Okay, so what quantum mechanics says or the quantum theory says, okay, a monochromatic beam of X-ray, if I will consider a monochromatic beam of X-ray of frequency nu, okay, this actually consists of photons of energy what? If nu is the frequency, h nu, or you can write h bar omega is the energy, right? And if you want to write the momentum, so E is equal to h nu. Nu is the frequency of the incident photon and h is the Planck's constant, so you can write it as h nu or h bar omega, right? Or else in terms of momentum, I mean in terms of momentum we can write P is equal to h bar k, so as per the quantum theory. So the Compton scattering is explained by considering it as a process of elastic collision between what? Between the X-ray photon. If you will consider it to be a elastic collision between what? The X-ray photon, the incident photon of X-ray, and a free electron, almost free electron, okay, which is very loosely bound. So free electron, but it is, as we are considering the electron in a particular matter, this is actually at rest, but it is free. So free electron loosely bound, but it is at rest. Now we will consider these two elements like X-ray photon and the free electron are undergoing some elastic collision. Okay, so now considering this collision, okay, what will happen? The photon will transfer. If there is a photon we said and a free electron, there is a collision, elastic collision between them, then photon will transfer some of its energy, okay, to the electron, and therefore the scattered photon, so some amount of energy is given to the electron, so whatever energy is remaining, right? So that energy, or in terms of frequency, if you will see, suppose I will write this to be some E prime, right, is the remaining energy. So here E prime we said will be definitely less than E, right? And hence if I'll write H nu prime, right, must be less than, you can write this to be H nu. So you can see that nu prime is less than nu. So we can write nu is equal to your, we know that V is equal to F lambda. For a wave, V is equal to F lambda, right? Or nu lambda, sorry. Nu we are writing for frequency. So nu is equal to V by lambda. For any electromagnetic radiation, we can write this is C by lambda. C is the speed of light. So let us write that way. Nu prime is less than nu. So we can write C by lambda, okay? Prime will be less than C by lambda. So here you can see C by lambda prime is less than C by lambda. We can write lambda prime must be greater than lambda. So this is what we can say. So a simple explanation just by considering what? The particle nature of, considering the particle nature of the incident electromagnetic radiation or the X-ray. Okay, so considering it to be a photon and its interaction with the electron as an elastic collision, we can say some amount of energy is like lost, So by this X-ray photon, okay, transport to the electron, and hence we said the energy carried by the photon after this collision is less than the original value that it was carrying before. So that way we can show this lambda prime is greater than lambda. Okay, so using this quantum model or quantum theory, we can easily explain this longer component of lambda that is present in the scattered radiation, or the Compton component of the wavelength in the scattered radiation can be explained. Okay, so now suppose let us do little math to understand what is that change in wavelength when I said del lambda is equal to lambda prime minus lambda. Okay, let us try to understand what is this Compton shift. Okay, suppose that the energy and momentum of the scattered photon we will consider scattered photon. Okay, we will consider to be h bar omega prime. Oh, and this is the energy value of the scattered photon E prime we said, and the momentum similarly suppose it is P prime. Okay, and then you can write it as h bar k prime. Okay, this is the momentum and this is the energy of the scattered photon, right? So the energy and momentum of electron, similarly the energy and momentum of the electron before the collision can be written as energy we can write as the electron is considered to be rest and free. So we can consider the rest mass of the electron to be m0. So the equivalent energy can be written as m0 c square, right? And the momentum, as we said, it is at rest, we can consider the momentum to be 0. So this is the energy of the electron and this is the momentum of the electron, whereas h bar omega prime is the energy of the photon, incident photon, sorry, the scattered photon, and h bar k prime is the momentum of the scattered photon. So this way we can start. So now we can say if the electron, okay, possesses momentum after the collision. What is the momentum? Okay, so after the collision, suppose the momentum of the electron we will consider to be Pe, and its energy, if you will write, because electron is a relativistic particle, photon has already given some energy to the electron. Now the electron will start moving in a different direction. So the energy can be written for a relativistic particle Pe, that is momentum of the electron, c square plus m0 rest mass of the electron, c square, right? So m0 c square to the power square this way, or you can write m0 square c fourth and to the power 1 by 2. This is the energy for the relativistic particle, right? So this way we can write. Now considering these two, like states before collision and after collision, knowing the energy and momentum value before collision and after collision, we can further write this to be what? So energy of photon, we said incident photon was what? H nu or h bar omega, right? Momentum of the photon, because photon is having zero rest mass, so its rest mass is zero. So we can write E is equal to, actually if I'll substitute like P square C square plus M0 square C4, just now I wrote, okay, to the power 1 by 2, and you substitute M0 to be 0 here for the photon, then we can write this to be P square C square to the power 1 by 2. That gives us PC, right? So we can rewrite it. P is equal to E by C, that is H nu by C, or we can write H bar omega by C, that is H bar K, because we know omega by C is equal to K, right? Since omega by C is K, right? So this way, now let us use the principle of conservation of energy, right? And then rewrite, I mean, the whole equation before and after the collision, right? So let us use the conservation of energy principle for this elastic collision. So conservation of energy for the elastic collision. So if it is elastic collision, then its kinetic energy and momentum both will be conserved. So let us write what was the energy before collision. So before collision, the photon has an incident energy of h bar omega, right? And the electron was considered to be at rest. So its energy will be the rest energy, rest mass energy. So m0 c square, that is equal to, after the scattering, after the collision, the photon got scattered, and it's having some energy. We said h bar omega prime plus the energy of the electron that we said, okay, is given by, we will write this to be what, p times c. So let us write this way. So this here for relativistic particle, p square plus m0 square c square. So here I just wrote, this is the thing actually, p square c square plus m0 square c fourth to the power 1 by 2. You just write this way, or you just take c out and then you write. Okay, so here now we can write what is this, pe square plus m0 square c square, this term, okay, can now be written as, you can just arrange it, h bar omega divided by c minus h bar, you got this h bar omega over here, then you got minus h bar omega prime and divided by c, then you have this m0 c square divided by c. So that way we can write, so h bar omega by c minus h bar omega prime divided by c, this is 1, plus you have that m0 c square divided by c, that gives you m0 c, right? It was under square root, so this whole thing will be now squared. Okay, so that will give us pe square plus m0 square c square, right? Now h bar omega by c can be written as what? This is nothing but h bar k, and h bar omega prime by c will give us h bar k prime, right? This is in the bracket, and then we have m0 c, okay, and whole square. Fine. Let us now rewrite it again to further simplify it. So from this equation, we can write what is PE square. Okay, taking that m0 c square to the right hand side and then opening the bracket. Let me just write it again and then rewrite the previous equation once again. M0 square c square, we got this gives us h bar k minus h bar k prime, okay, plus m0c and then whole square, right? So I'm rewriting it for p square. So I will write h bar square and opening this whole thing. This is considered to be a and this is b, a plus b whole square. That way you can write. So h bar can be taken common. So h bar square, then you have k square, k minus k prime whole square you got. So minus 2k k prime plus k prime square, right? Plus 2ab you have, so 2 times m0 c h bar and then k minus k prime, right? This whole thing we got. Okay, so now we are done with the conservation of energy. We got this pe square to be this using the conservation of energy principle. So conservation of energy we used here, right? Now let us use the conservation of momentum, right, in the vector form. Okay, so law of conservation of momentum, if you will apply, of momentum in vector form, in vector form, then we can rewrite the, we can write the conservation of momentum as what? H bar k, that is the momentum of the incident photon. The electron was at rest, so momentum was 0, is equal to pe, I'm writing for the momentum of the scattered electron, plus the scattered photon momentum is h bar k prime, right? So that from here we can write pe can now be written as, or pe square, because I need just to solve this by equating. So pe square we can simply write, this is h bar and k minus k prime whole square, right, which can be written as h bar, sorry, h bar square, because I squared both the sides. Then we can write this to be k square plus k prime square, and then here minus 2k k prime cos theta, because we are considering the vector form, right? So k minus k prime whole square, if you write, this is nothing but k minus k prime vector dot k minus k prime. So that way you can write, This will give us k square plus k prime square minus 2k prime cos theta. Right now, the cos theta, the theta is the angle between this k vector and k prime vector. So k vector is the direction of, or the velocity or the momentum, direction of the momentum of the incident photon. This is k, you said. And if it is scattered in one, in a certain direction, then what is the angle made by this scattered one, k prime, because that's the momentum for the scattered one, right? So this angle is theta here. So p square gives you h bar square, k square plus k prime square minus 2k prime cos theta. So we have two equations, p square, and here also another p square. We can equate these two. Okay, so if you equate these two, what we will get, just by equating equation 1 with equation 2, we can write it just h bar square. The first equation was k square minus 2 k prime plus k prime square plus 2m0 c h bar k minus k prime, that is equal to, from the conservation of momentum in vector form, we got this h bar square. This is k square plus k prime square minus 2k prime and cos theta. Okay, so now solving this equation, you can just write whatever is common, cancel those, and then rewrite plus 2m0 c h bar k minus k prime is equal to minus h bar square 2k prime cos theta. Okay, further rewriting, you can write m0 c h bar k minus k prime is equal to, take to one side and take whatever you can take common, h bar square k prime. Okay, if I'll take, then I got here, this gives us 1 minus cos theta, right, this way. So further rewriting, we can write it as k minus k prime divided by k prime, that is equal to h bar divided by m0 c 1 minus cos theta. Okay, so 1 by k prime, just by taking k by k prime minus k prime by k prime, you can rewrite this 1 by k is equal to h bar by m0 c into 1 minus cos theta, right? So k is equal to 2 pi by lambda, the wave vector, we know that. So substituting that, 1 by k prime will be now lambda prime by 2 pi minus lambda by 2 pi is equal to h bar. H bar simply is the same way. If I want to write in terms of 2 pi, let me just write h by 2 pi, which is your h bar, right? We can write that, and then m0 c and 1 minus cos theta. So you can see 2 pi in both the sides, so cancel those. Then you got lambda prime minus lambda is given by h by m0 c, okay, multiplied with 1 minus cos theta, right? So this lambda prime minus lambda is nothing but the Compton shape, right? So that we can rewrite what is del lambda. Del lambda is equal to, actually what we got, h by m0 c. H is Planck's constant, m0 we got the rest mass of the electron, and c we know that speed of the electromagnetic radiation, and then 1 minus cos theta. Cos theta is the angle between k and k prime, that is initial momentum of the incident photon and the scattered photon. What is the angle between them? That is 1 minus cos theta. Okay, so this thing can also be rewritten this way. We can also write this del lambda to be what? We got h by m0 c, which also can be written as 2 pi h bar divided by m0 c. So h by m0 c, this gives you, if I will write 2 pi h bar, okay, that means you are writing 2 pi and h by 2 pi, so it's the same thing, h by m0 c. So another way of writing it, you can write cos theta as it is. So here this thing is written as lambda c. Okay, lambda c I wrote for 2 pi h bar divided by m0 c, and then 1 minus cos theta. Okay, this is our Compton shift, can also be written this way. And this lambda c here, okay, is h divided by m0 c, or 2 pi h bar m by m0 c, whatever we want to write. Okay, and these are all constant value. H is known, m0 is known, c is known. If you will substitute all these values, it gives you 0.0243 angstrom. Angstrom is 10 to the power minus 8 centimeter, or 10 to the minus 10 meter. So we got our Compton shift. Okay, the value of Compton shift in terms of lambda c, which is a constant. So 0.0243 multiplied with 1 minus cos theta, and this lambda c is known as Compton wavelength. We call this to be this constant. Okay, we in terms of unit of distance you got, so that is known as Compton wavelength. We define this to be Compton wavelength, okay, of the electron. Compton wavelength of the electron. Okay, so the Compton wavelength of an electron is nothing but the wavelength of radiation, the wavelength of radiation whose photon has energy equal to the rest energy of the electron. So what do you mean by this? So we define the Compton wavelength lambda to be what? To be the what wavelength of radiation whose photon has energy equal to the rest photon energy is equal to the rest energy of the electron. So how we will do that? See, let us define this lambda c this way. So we said h nu. Okay, so h nu is what? The energy of the incident photon, right? H nu is equal to what? The rest energy of the electron, that is m0 c square, right? So from this you can see, you can just write it, hc by lambda is equal to m0 c square. So if you will write what is lambda, lambda is equal to h by m0 c. This is what our lambda c is, right? So you can also define Compton wavelength this way. Okay, this h by m0 c is nothing but what? The Compton wavelength of the electron. Okay, and the Compton wavelength of the electron you can get by just what? By just taking or equating the energy of the incident photon with what? The rest energy of the electron. Okay, so that gives you the value. Finally, we got our del lambda, the Compton shift, given by lambda c, which is h by m0 c, we said, and 1 minus cos theta, right? This particular equation clearly shows that the Compton shift del lambda is independent of what? Independent of the wavelength of the incident radiation and the nature of the target material, the nature of the target material on which it is incident. Okay, suppose this is target material and you have the incident photon, okay, and incident and encountered one electron, and then it is scattered in a certain direction, and the electron, you got the electron to be scattered in this direction. So we said the incident photon, the energy was h bar omega here, and here we consider to be h bar omega prime, and the momentum we consider this to be h bar k, and the momentum here we considered h bar k prime, the momentum here we considered pe, right? And the energy we consider to be pe c square plus m0 square c fourth, okay, to the power 1 by 2. This is the energy of the relativistic particle, because electron is a relativistic particle. So considering it to be a elastic collision, you can easily show the presence of the longer wavelength, okay, lambda prime, in the scattered radiation here, in the scattered radiation, right? And the unscattered radiation is the lambda, right? The Thomson component. The longer component of wavelength that you are getting is known as the Compton component. Okay, so this is all about your Compton effect or Compton scattering. Thank you for watching.